Hello friends, in this lecture we will discuss Taylor's theorem. You all know Taylor's theorem in real analysis. The same Taylor's theorem and Maclaurin's theorem. Same Taylor's theorem is also valid in complex variable or complex analysis. The Taylor's theorem we have seen for x belongs to R. Now we want to see for z belongs to C. Right? We want to go for z belongs to C. In UG course, you have seen Taylor's theorem, Maclaurin's theorem, Lorentz series in the real variables. Now we'll go in the complex variables. Now what is the statement of first result? If f is analytic in the disk having center, origin, radius r, then f has a Maclaurin expansion. F of z is equal to summation n greater than or equal to 0 an z raised to n for all z in the disk, where an equal to fn at 0 means nth derivative of f at z equal to 0 divided by n factorial, and which is also equal to 1 upon 2 pi I integral over gamma f of xi upon xi to the power n plus 1 into dz. The same thing can also be written as integral over gamma f of z upon z to the power n plus 1 dz. Both are same, no doubt. Only we have taken this z. That can be interchanged. For n equal to 0, 1, 2 and etc. with gamma is a set of all those points so that mod z equal to r. That means set of all those points lies on circle having center at origin and radius small r, where this small r is strictly less than capital R. So this disk is this is the disk, open disk having center at origin and radius r, while this is a circle, right, having center, origin again and radius small r, and this is about capital R. In this disk we have considered this circle as a gamma. Gamma is the set of all those points lies on this circle. Okay, so what is the result says? If f is analytic in this disk, right, then f has a Maclaurin series expansion f of z equal to summation from n is greater than or equal to 0, or this can be written as a0 plus a1z plus a2z plus a3 a2z square plus a3z cube and up to so on, in up to infinite. Here upper limit is what? Infinity. In the power series also upper limit was infinity. Okay, f of z equal to summation n greater than or equal to 0 an z raised to n for all z in the disk, where an these coefficients are obtained by using this formula, nth derivative of f at z equal to 0 divided by n factorial. And already in power series we have discussed an is given by 1 upon 2 pi I integral over gamma f of z upon z raised to n plus 1 dz, or f of xi upon xi to the power n plus 1 dz, with gamma is a circle having center at origin, radius small r, and that radius is strictly less than capital R. We'll go for this. For a given z in this disk, we choose small r such that small r is less than r, and let gamma is a circle having center, origin and radius r. We know the Cauchy's integral formula, f of z equal to, if this holds, then f of z is equal to 1 by 2 pi I integral over gamma f of xi upon xi minus z dz. There was the formula for f of a also. If a is lies inside this disk, then f of a equal to 1 upon 2 pi I integral over gamma f of xi upon xi minus a dz. This was the Cauchy's integral formula. So replacing a by z, we get f of z equal to 1 upon 2 pi integral over gamma f of xi upon xi minus z into dz. We know that for all this r upon xi less than 1, because this is what? This is equal to mod xi equal to r. Mod xi equal to r. Okay, so let xi having radius r. Therefore, r upon xi. What is it? Z upon xi. I think this is Z upon xi. Okay, not r. This is Z upon xi. Where Z we have taken? Z is in the delta r. So Z can be taken anywhere inside this outer circle, this disk. So what about this Z? If I take distance between this and this, obviously mod Z, what will happen? If I take here, mod Z will be greater than mod xi. That is, mod xi will be less than mod Z. And therefore, mod of xi upon Z will be less than what? 1. Mod of xi upon Z. Here it should be mod of 1 minute. Okay. Where we have taken delta r, choose r. Okay. F of z 1 by 2 pi I. Right. It should be your point inside z. If z is inside this one, then we have that. So z we have taken here. Right. In that case, your mod of z upon mod z will be less than mod xi. Mod z will be less than mod xi. Therefore, mod z by xi will be less than 1. So this is mod z by xi less than 1. So 1 upon xi minus z can be written as 1 upon xi into 1 upon 1 minus z by xi, which is just representation of this one. If I take 1 by xi common, what about this? Xi minus z upon xi, xi cancel, we get xi minus z. That can be written as 1 by xi upon 1 minus z by xi. And we can write this in the form of what? Power series expansion, as like 1 upon 1 minus x. 1 plus x square plus up to y for this as where mod x is less than 1. That we have, which is summation n greater than or equal to 0 x to the power n. In the same way, what about this? 1 by xi into z by xi to the power n for n greater than or equal to 0. For n greater than or equal to. So this will give us summation for n greater than or equal to 0 z to the power n upon xi to the power n plus 1. So 1 upon xi minus z is this. Summation for n greater than or equal to 0 z raised to n upon xi to the power n plus 1. And convergence is uniform on gamma and for fixed z and for a fixed z. Now f of xi is bounded on gamma since it is continuous on the compact set gamma. As it is differentiable, it should be continuous, and continuous function on bounded region is also function is bounded. Okay. Now let f of xi equal to f of xi upon xi minus z equal to summation over n greater than or equal to 0 fn of xi with fn of xi is equal to f of xi upon xi to the power n plus 1 z raised to. Why we are saying like that? Because 1 upon xi minus z is summation over n greater than or equal to 0 z raised to n upon xi raised to n plus 1. We are multiplying that with only f of xi. So that I have written f of xi. And therefore fn of this whole term independent of n, that I have taken fn of xi. That will get f1 of xi, f2 of xi, f3 of xi, and so on. Above series again converges uniformly on this gamma, because that gamma is a circle having center, origin, radius small r, and that small r is strictly less than capital R, where that capital R is the radius of convergence. Indeed, in closed disk having center, origin, and radius rho, f of xi is bounded for each row, which is again strictly less than small r. If I take a closed disk here, it will happen. Here we have taken a again closed disk having center something rho. Okay. With bound capital M, say. Therefore, mod of fn xi less than or equal to supremum over xi is equal to rho Fn of xi, right? Supremum of this over xi is equal to rho, which is less than or equal to capital M rho to the power n upon r to the power n plus 1. Why rho to the power n upon r to the power n plus 1? Because mod xi equal to small r, so it becomes r to the power n plus 1. F of xi we have considered upper bound m, so it is m, and z raised to n we have taken that point here, so rho to the power n. So m upon r, rho by r to the power n. Therefore, by Weierstrass test, the series for all n greater than or equal to 0, Fn of psi converges uniformly, because rho by r less than 1. Rho by r is less than 1 because rho is inside again that r. This is the original disk having center r. Then we have taken inside circle having radius r, and then we have taken inside disk again having radius rho. So obviously rho by r less than 1, and therefore this is less than 1, and if it is less than 1, then this is converges uniformly. What is Weierstrass test? If summation over n greater than or equal to n mn be the convergent series of positive real numbers such that mod of f n z less than or equal to mn for all n belongs to n and for all z in a setting, then this series converges absolutely and uniformly in D. Therefore, by using this result, we have taken the series converges uniformly. Therefore, the series summation n greater than or equal to 0 fn of psi may be integrated term by term. Therefore, 1 upon 2 pi integral over gamma f of xi upon xi minus z into d xi is equal to, again summation n greater than or equal to 0, 1 upon 2 pi integral over gamma f of xi upon xi to the power n plus 1 d xi into z raised to n. Again it is only substitution, okay, f of xi, which is equal to n greater than 0 equal to 0 a n z raised to n. We have taken this as a n z raised to n. Since z is in the disk having center at origin radius capital R is arbitrary, we have f of z or f of z equal to summation of a n z raised to n for all n greater than or equal to 0 and for all mod z less than r. So the assertion now follows from Cauchy's integral formula for derivatives. Uniqueness of coefficients a n follows from the uniqueness theorem for Taylor series. The value of integral is independent of the choice of curve in mod z less than r. Mod z less than r. So what we have proved, that f of z can be written as summation for n greater than or equal to 0 a n z raised to 0, which is given by this and which is also given by this one, isn't it? So a n becomes this one, right? Okay. So this is your Taylor's theorem. What says Taylor's theorem? If f is analytic, then f of z can be written as in this way for all a n. This a n is power series, from power series. We have already written there. From power series, this a n can be calculated by using this. Here we have calculated a n by using this because this coefficient we have taken into z raised to n, and therefore a n is this one. That is there. Summation this term into z raised to n, therefore this should be your a n and also equal to this one. This is called Macalurin series, okay. Taylor's theorem, if f of z is analytic in a domain D, then for z belongs to a disk having center A, radius r, which is subset of D, f has the Taylor series expansion. Only z raised to n is replaced by z minus a. So rather than considering center origin, we are considering here center any arbitrary point A, and the expansion is called Taylor's theorem, where a n is nth derivative of f at a now divided by n factorial, not 0, and which is equal to 1 upon 2 pi r integral over c f of xi upon xi to the power n plus 1 replaced by xi minus a to the power n plus 1 into d xi, where again c is the circle having center at a and radius is r. So what is the difference between Macalurin and this one? Here we are considering the disk having center at a radius capital R. There we have considered the disk having center at origin, radius is capital R. That is the only change. And therefore we are replacing z minus 0 by z minus a. So using the transformation z minus a equal to w, we obtain the above result. What we have to do only? We have to take z minus a equal to w. We will obtain that result. Okay. Z minus a equal to w. We will get this one. For example, we know that f of z equal to log of 1 minus z is analytic in the cut plane C, derived from or apart from x plus I0 for x greater than or equal to 1. In particular, f is analytic in mod z less than 1 and has a Taylor series. Every function which is analytic in given this, then it has a Taylor series expansion in mod z less than 1 about O f of z equal to summation from n equal to 0 to infinity a n z raised to n, where a n equal to f n at 0 upon n factorial. What we are saying here? What about log of 1 minus z? Log z, where log z is defined. We know that only log z is defined in this, right? Negative values for log are not defined. Therefore, it is defined in the cut plane, whole complex plane C derived from x plus I into 0. What is x plus I into 0? This is only x. X means here on real axis, where x greater than or equal to 1. X greater than or equal to 1. That is the case. So log of 1, if I take 1 minus z is there. So we have, this is 1 and this is minus z. So if I take z equal to 1, that is 1 plus I into 0. What will happen? Log 0. Log 0 is indefinite. Log 0 is indefinite. Okay. If I take x greater than 1 and suppose I take 2 plus I into 0, what will be here? Log of 1 minus 2, that is minus 1, which is not defined again. Log of minus real number is not defined, and therefore we are taking like this. So you have to remove all these points from C. Then f of z is defined. We have to remove x plus I0 for x greater than or equal to 0 from complex number. Then our log of 1 minus z is defined. Otherwise, for these values, it is not defined. What about here? The set of all those numbers of the form x plus I0 means x, and where x greater than or equal to 0. Suppose this is 1. X greater than or equal to 0 means what? In this way. These are x greater than r. So we will drop this from our C and then log of 1 minus z. From this region is our x greater than or equal to 1. Correct? See here. Suppose this is x equal to 1. Then this region is x greater than or equal to 1. So we will consider this as the whole part. C minus x plus I0 for x greater than or equal to 0. Okay. In particular, so in that region now, your log of 1 minus z is analytic. Where log of z is analytic? Log of z is analytic for all positive terms. All positive terms. What is log of mod z is equal? We know that it is mod z. Log of z equal to log of mod z plus I into argument of z. That we have to know. And mod z means it is always positive. So it should not be equal to 0. For z equal to 0, it is not defined. And for which it is not also defined. For z equal to 0, it is not only defined. Or in other cases, it is defined. So that's why we are taken. So it has a Taylor series expansion. So it must have a Taylor series expansion, this one, having a n equal to f n at 0 upon n factorial. Note that 1 is the largest number, so that f extends to be analytic in the disk mod z less than r. It follows that f of 0 equal to log 1 equal to 0. F of 0 is what? Log 1. Log 1 is 0. And for n greater than or equal to 1, f n at 0 equal to. Now, what is f dash at 0 here? F dash at z equal to derivative of log of 1 minus z. It is 1 upon 1 minus z into derivative of 1 minus z is minus 1. This is f dash at z. What about f double dash at z? Again, this minus 1 into, again derivative of 1 upon 1 minus z. So it is minus 1, means 1 minus z to the power minus 1. Minus 1 into 1 minus z to the power minus 2 into again minus 1. So what you are getting here? Minus, minus and minus. So we get again minus there upon 1 minus z to the power 2. 1 minus z to the power 2. Isn't it? If I take its derivative again, f triple dash at z becomes minus 1 into, this is 1 minus z to the power minus 2. So it becomes minus 2 upon 1 minus z to the power plus 3 into again minus 1. Isn't it? So you will get here minus 1 minus 2. That is minus 1 minus 2 minus. So minus is again common and we get 1 into 2 upon 1 minus z to the power 3. So in general, nth derivative will be minus into 1 into 2 up to n minus 1 divided by 1 minus z to the power n. And at z equal to 0, if I put, so fn at 0 becomes minus into 1 into 2 up to n minus 1 divided by 1 minus z to the power n at z equal to 0. Now what will happen at z equal to 0? It becomes minus of 1 up to n minus 1, that is n minus 1 factorial. So minus of n minus 1 factorial. So for mod z less than 1, log of 1 minus z equal to minus summation from n equal to 1 to infinity z raised to n upon n. Why z raised to n upon n? What is an? Fn at 0 is, what is an? An is fn at 0 upon n factorial. What is fn at 0? Minus of n minus 1 factorial upon n factorial. This is our an into, so this is our an. What about this now? Minus of n minus 1 factorial upon n factorial, is it is only 1 by n. So an is minus 1 by n. So minus outside 1 by n into z to the power n from 1 to infinity. Okay, here an is minus 1 upon n. You can find it's a radius of convergence also. Therefore, limit as n tends to infinity, supremum of an to the power n 1 by n equal to limit as n tends to infinity, supremum of mod is plus now 1 by n to the power 1 by n, and this will gives us 1. As n tends to infinity, this will gives us 1, and which is 1 by r. So r is 1. So radius of convergence is 1. That is, the series converges absolutely for mod z less than or equal to rho, which is strictly less than 1. Isn't it? We don't know what about at mod z equal to 1. So for mod z equal to 1, this becomes 1 by n, which is divergent. For mod z equal to 1, this is 1 by n, which is diverges. Okay, that we can write. So what is the use of Taylor series? Taylor series gives us the power series representation for analytic function. Power series representation for analytic function. This is one more example, because power series representation we have obtained there. Okay. G of z equal to log of 1 plus z upon z. This is analytic in D, where D is derived from x plus I0, and now x is less than or equal to minus 1 union 0. So this G is defined in C. If I remove these from that C, if I remove this from that C, how? At 0, this is not defined. If x is less than or equal to minus 1 and x plus I0, for such all points, this becomes 0, correct, or negative. This becomes 0 or negative. If I take x equal to minus 1, this, that is z equal to minus 1, so this becomes 0. If we take less than minus 1, then log of 1 minus minus 2. It will get log of negative terms. So in that case also not defined. And therefore we are removing these points from C and at those points log of 1 plus z upon z is log of 1 plus z upon z is always defined. Though at z equal to 0, gz here is not defined, but g can be extended to analytic at z equal to 0 because log of 1 plus z is summation n from 1 to infinity minus 1 raised to n minus 1 z raised to n upon n for mod z less than 1. Log of 1 by z can be written in this way. Why log of 1 by z can be written in this way? For mod z less than 1, we know that log z means log of 1 by z, you can find a and there. What is first derivative? 0th derivative means first derivative is what? 1 upon 1 plus z. What is the second derivative? Minus 1 upon 1 plus z square, isn't it? What is the third derivative? Minus 1 minus 2 upon 1 plus z to the power 3 and so on. So nth derivative becomes minus 1 raised to n minus 1 into n minus 1 factorial, right, divided by 1 plus z to the power n. 1 plus z to the power n. What is f? N at 0, it becomes minus 1 raised to n minus 1 into n minus 1 factorial. And what will be an? Fn at 0 upon n factorial. So divided by n factorial. So we get minus 1 raised to n minus 1 upon n. Minus 1 raised to n minus 1 upon n into z raised to n for mod z less than 1. This is log of 1 plus z. Therefore, log of 1 plus z upon z becomes, dividing this by z, z raised to n minus 1 for mod z less than 1. So log of 1 plus z upon z is the power series summation n from 1 to infinity minus 1 raised to n minus 1 upon n into z to the power n minus 1, z to the power n minus 1 and so on. Okay, that is the case. Here log z is considered and z is replaced from this. For negative z it is not defined, so z is defined for all c removing x plus I 0 points where x is less than or equal to 0 and a equal to minus 1 plus I. If I take a point, that is minus 1 plus I, isn't it? Minus 1 plus I, which is equal to, we know that every complex number can be written r e to the power I theta, where r is the mod of z and theta is tan inverse of y by x. We know this. So from this, what about mod of this point? Square root of 2 and e to the power I theta. Theta is what? Tan inverse of y by x. Tan inverse of 1 upon minus 1, which is 3 pi by 4. Okay, that we have taken. Then f of a is log of minus 1 plus I, which is equal to log of mod of this plus I into argument of this, which is equal to square root of 2 into argument is 3 pi by 4 I. Also for n greater than or equal to 1, fn at z equal to, it's the nth derivative, minus 1 to the power n minus 1 into n minus 1 factorial upon z raised to n, and an is fn at a divided by n factorial, which is equal to minus 1 raised to n minus 1. Now we are finding it's a Taylor series expansion about z equal to a, any point a, where a is this complex number. Okay, so an equal to fn at a upon n factorial. Put z equal to a there. What will happen? Minus 1 raised to n minus 1, right, into n minus 1 factorial into n minus 1 factorial upon z raised to n means a to the power n divided by n factorial, So fn at a upon n factorial is there. So if this divided by n factorial means we get only n division, minus 1 raised to n minus 1 upon n, z raised to n. Now this divided by z raised to n we have replaced by. Now what is z? Z means what? This one is. So r raised to n, that is root 2 to the power n, 2 to the power n by 2, into e to the power 3 pi I by 4. So that will goes in the numerator, e to the power minus 3 pi I by 4 you get. Okay, nth of this, it's a nth power, right? It's a nth power. That is the case. Therefore, the power series expansion of f about a is f of z equal to summation from n equal to 0 to infinity minus 1 raised to n minus 1 e to the power minus 3 pi I by 4 upon n into 2 to the power n by 2 into z minus a to the power n. Actually, as this is z, z raised to n, z raised to n means a raised to n. If a is this one, a is a to the power n is square root of 2 3 pi I by 4 to the power n, isn't it? So this should be your 2 to the power n by 2 into, we have taken this 3 pi I e to the power 3 pi I by 4 to the power n. That means e to the power 3 pi I n by 4. It should be n here somewhere. 3n pi I by 4. It should be 3n pi I by 4. 3n pi I by 4. Okay, it is like that. Now limit as n tends to infinity, supremum of this one, a n to the power 1 by n, you will get supremum of 1 upon n 2 to the power n by 2 upon 1 by n, because this modulus is always equal to 1. Whatever n is there, e to the power I theta is always equal to 1. This modulus is again 1. So we have to take modulus of this term and it's a supremum. So n into 2 to the power n by 2 to the power 1 by n. N cancels with n. We get n into 2 to the power 1 by 2. As n tends to n to the power 1 by n is 1, and 2 to the power n by 2 to the power n by n is 2 to the power 1 by 2. That is 1 upon square root of 2. So this is our 1 by r, and therefore r equal to square root of 2. Therefore above series converges in mod z minus a less than square root of 2, and therefore the radius of convergence is what? Square root of 2 there. Radius of convergence is square root of 2. We have this function also, f of z equal to z to the power minus 1. Then f is analytic on c removed from 0. Therefore for all z not equal to 0, f n at z equal to minus 1 raised to n into n factorial upon z raised to n plus 1. Why? Because f z equal to 1 by z. 1 by z means z raised to minus 1. What is f dash z? Minus 1 z raised to minus 2. What is f double dash z? Minus 1 minus 2 z raised to minus 3, up to so on. So what will be f n z here? Minus 1 minus 2 up to minus n, minus 1 minus 2 up to minus n minus 1. See here, minus, this is for 1. F double dash z is what? Minus 1 into z raised to minus 2. F dash z is minus 1 there. F double dash z is minus 1 minus 2 into z to the power minus 3. So f n at z is what here? Minus 1 minus 2 up to minus n into z raised to n plus 1, minus of n plus 1, that is z raised to n plus 1. So this is minus 1 raised to n into n factorial upon z raised to n plus 1, f n at z. So you will get this one for n equal to 0, 1, 2 up to so on. Thus the Taylor series expansion of f about z equal to 0 is given by 1 by z summation n greater than an about z0 which is not 0. So f n at z0 upon n factorial, that n factorial cancels with n factorial, we get minus 1 raised to n upon z0 to the power n plus 1 into z minus z0 to the power n, where z belongs to a disk having center at z0 and radius mod of z0. Radius mod of z0. Using k-fold differentiation is there, you are writing something there. Let us develop a function f defined by f of z equal to 1 upon 1 minus z square into a Taylor series about 0. So if such function is there, then we can find it's a power series expansion. We can find it's a power series expansion. A Taylor series expansion about 0. Taylor series expansion about 0. By the partial fraction, we have f of z equal to 1 upon minus of z square plus z minus 1. That we have written minus of z square plus z minus 1 only. Okay. Which is equal to 1 upon minus of z square plus z perfect square. We are making perfect square. Z square plus z plus 1 by 4 minus 1 by 4 minus 1. This is very 5th or 6th standard. 1 by 2 coefficient of z, it's a square. Adding and subtracting. Equal to 1 upon minus of, now this is a z plus 1 by 2 square. And this is your minus 5 by 4. If I take outside, we get plus 5 by 4. That is root 5 by 2 square minus z plus 1 by 2 square, which is equal to 1 upon root 5 by 2 minus z plus 1 by 2, that is minus z minus 1 by 2 into second bracket root 5 by 2 plus z plus 1 by 2. That is 1 upon, now you have to take this one, root 5 minus 1 upon 2 minus z root 5 plus 1 upon 2 plus z. That is minus 1 upon, I have taken minus common, z minus root 5 minus 1 upon 2, z plus root 5 plus 1 upon 2, minus 1 upon, you can write z minus alpha, z minus beta, where alpha is root 5 minus 1 by 2, beta is what? Minus of root 5 plus 1 upon 2. So we have to make partial fraction here, and for that partial fraction you can write this as 1 upon beta minus alpha, 1 upon z minus alpha minus 1 upon z minus beta. How? Cross multiplication, z minus beta minus z plus alpha, that is minus beta plus alpha will be in the numerator, and in the denominator this will be z minus alpha, z minus beta, isn't it? So if I take minus common from that, we get beta minus alpha, cancels with this, we get this one. So 1 upon beta minus alpha into this can be written as 1 upon beta into 1 upon 1 minus z by beta. 1 by beta, if we take from that, what you will get? 1 upon 1 minus z by beta. See here, what will happen here? For this only, we have taken common here. What about 1 upon beta? This will be beta minus z upon beta. That cancels with this one. So we get 1 upon beta minus z. But this is minus 1 upon z minus beta. That we have written plus 1 upon beta minus z. Okay. So second term is written in this way, and first term is written in this way. Note that alpha is less than mod beta. Alpha into beta is minus 1, and beta minus alpha is minus of root 5. Isn't it? Alpha is less than mod beta. If I take mod of beta, then this alpha will be strictly less than mod of beta. You find mod of beta there. What is mod of beta? Root 5 plus 1 by 2. And root 5 plus 1 by 2 is always greater than root 5 minus 1 by 2. So that we have taken. If I take product, root 5 minus 1 by 2 into beta minus of root 5 minus 1 by 2. So it will get minus into bracket root 5 minus 1, root 5 plus 1. That is 5 minus 1, 4. 4 by 2. Root 5 means root 5 into root 5. That is 5 minus 1 divided by 2 into 2, 4. So we get 4 by 4, that is 1, and this minus sign. Beta minus alpha, if we take beta minus alpha, you will get minus of root 5. Therefore, by the Taylor series of f about origin is f of z is equal to 1 upon beta minus alpha into summation n greater than or equal to 0 for this z raised to n upon beta raised to n plus 1, isn't it? Minus summation n from n greater than or equal to 0 z raised to n upon alpha raised to n plus 1 for this, because it is of this form 1 by beta upon 1 minus z by beta, and this is 1 by alpha upon 1 minus z by alpha. So it is of this form alpha upon 1 minus alpha if alpha is less than 1, mod alpha is less than, and its summation is what? This one, z raised to n upon alpha raised to n plus 1, isn't it? This way. So summation n is greater than or equal to 0, z raised to n upon beta raised to n plus 1 minus summation n greater than or equal to 0, z raised to n upon alpha raised to n plus 1 mod z less than alpha. So it is 1 by root 5 summation from n greater than or equal to 0 beta to the power n plus 1 minus alpha to the power n plus 1 divided by alpha into beta to the power n plus 1. You are taking summation common and then z raised to n common. So we are getting 1 upon beta to the power n plus 1 minus 1 upon alpha to the power n plus 1. So we are getting that, isn't it? Minus alpha to the power n plus 1, alpha to the power n plus 1 minus beta to the power n plus 1 upon alpha into beta to the power n plus 1, that we have taken. And beta minus alpha is minus of root 5. That minus of root 5 is replaced by minus sign, z raised to n. So 1 upon root 5 into this one, mod z less than alpha. Since the first series converges for mod z less than beta, while second series converges for mod z less than alpha, so that combined series converges for mod z less than minimum of alpha and beta. I will take something alpha. Minimum of alpha and beta is what? Alpha is the minimum from these two. As alpha beta equal to minus 1, we have 1 upon 1 minus z square equal to 1 upon square root of 5 summation n greater than or equal to 0. This is a beta to the power n plus 1 minus alpha to the power n plus 1. Alpha beta is minus 1 to the power n plus 1 into z raised to n mod z less than alpha. Mod z less than alpha. Okay, that we have taken. You have used alpha beta equal to minus 1. So minus 1 to the power n plus 1, that we have. So this is our beta. What is beta is your, I think this is your beta, this is our alpha. 1 minute. What is alpha and beta? Alpha is root 5 minus 1 by 2. Minus of this one is alpha, isn't it? Root 5 minus 1 by 2 and beta is root 5 plus 1 by 2. Alpha is root 5 minus 1 by 2 and beta is big, and this sign becomes minus, so that you are taking this as 1 minus root 5 because it was root 5 minus 1, isn't it? So minus of that minus sign. So we have taken minus 1 to the power n plus 1 because of that. So you have taken z raised to n for mod z less than alpha. For mod z less than alpha, we may write 1 upon 1 minus z square as this one. That is 1 equal to 1 minus z square. This is in the product. Summation n greater than or equal to 0, an into z raised to n. So 1 minus z square into a0 plus a1z plus a2z square and so on. By uniqueness of coefficients of f about 0, on equating the coefficients of z raised to n on both sides, we see that a0 is 1, a1 is 1, an plus 1 is an plus an minus 1. Only you are equating both sides, isn't it? So if I find this product, 1 into this whole term, so a0 plus a1z plus a2z square, minus z into this whole term, minus a0z minus a1z square minus a2z raised to 3 and so on, minus a3 minus a0z square minus a1z cube minus a2z raised to 3 and so on, equating the coefficients of z. So here z raised to 0 is 1 is goes to 1. So a0 is equal to 1. a1 is also equal to, what about a1z? a1z minus a0z. a1z minus a0z will be there. Coefficient of z in the right hand side. And this is equal to 0. But a0 is what? a0 is 1. So a1z minus z equal to 0. So we get z into a1 minus 1 equal to 0. and so as z is non-zero, a1 should be equal to 1. So a1 equal to 1 again, and all other terms an plus 1 equal to an plus an minus 1. That is it is the Fibonacci sequence, isn't it? First term 1, second term 1, and the remaining terms are addition of previous two terms. That is called Fibonacci sequence, isn't it? 1 equal to a0 plus a1z. That is obtained there. So we see that this one is, so sequence of an is the Fibonacci sequence. Fibonacci sequence. This is the Fibonacci sequence. Okay, that we have written here. So 1 upon 1 minus z square can be written as 1 is equal to this one, and an is the Fibonacci sequence there. Fibonacci sequence. There are so many other examples whose Taylor series expansion can be found, isn't it? F of z, e to the power z, its nth derivative is again e to the power z, nth derivative at z0, e to the power z0, and therefore f of z equal to summation n greater than or equal to 0, f n at z0 e to the power z upon n factorial z minus z0 to the power n. You can again find Taylor series for sin z, Taylor series for cos z, and so on. So if I take sin z as a function, then it's a first derivative cos z, that is sin pi by 2 plus z. We know this. Then nth derivative sin z plus n pi by 2, and therefore f of z is nth derivative at z equal to z0 upon n factorial into z minus z0 to the power n. Similarly for cos z also you can find it. Its nth derivative is cos z plus n pi by 2. So its summation is cos z0 plus n pi by 2 upon n factorial z minus z0 to the power n, and therefore summation n greater than or equal to 0. If I take z0 is 0, then cos n pi by 2 upon n factorial z raised to n. So cos z can also be written as, we know that 1, if I put n equal to 0, you will get 1 upon 0 factorial into z raised to 0, that is 1, plus n, if I put n is equal to 1, cos pi by 2 is 0, so there will be no second term. N equal to 2, cos pi is minus 1 upon 2 factorial z raised to 2, and so on. You will get this. Similarly for sin z we get z minus z cube by 3 factorial plus z raised to 5 by 5 factorial minus, and so on. This will be Taylor series expansion about of sin z about z equal to 0. Okay, so there are some other examples, and you can go for these examples how to obtain the Taylor series representation for given functions. Okay, these are some examples which are for homework to you. We will stop here.